Okay, this is a review video for the Kaiser FIR filter design technique. This comes from an old exam problem, so it's a good thing to review. Alright, so what we have going for us here is we want to do a Kaiser filter design, and we're given a passband specification of 4 kilohertz, stop band specification of 4.5 kilohertz, and the operating rate of the filter. I'm specifying it here as 40 kilohertz, but we've talked about this before. That's the same thing as 40 kilosamples per second. Okay, so we have a stop band attenuation specification, 60 dB. So hopefully in your head you're seeing pictures that look like this. Okay, where we have a ripple specification, 0.05 dB. Okay, and then also stop band. These are all forbidden zones for the filter response. And this from 1 down is 60 dB. Okay. All right, so on the exam, I walked students through 4 steps for completing this problem. The first one is to specify the form of the desired response. Okay, so what you're supposed to know, and if you don't remember it, you should have it on your formula sheet. You're supposed to know D of K, the desired impulse response for a low-pass filter. Okay, so that's, we derived this in class, but it's sine omega C K divided by pi K. All right, so that's where we start. And then we take these specifications and we need to apply the specifications to get alpha and the order for the Kaiser window. Once we know alpha and the order, we essentially have the filter design. Okay? So that process involves looking at finding omega C. All right, so we know that F pass is 4 kilohertz. Okay, we know F stop is 4.5 kilohertz. Okay, so FC, the cutoff, is the midpoint between the two. Okay, so I can just eyeball that. I think you can too. 4.25 kilohertz. All right, and then we would convert that into normalized frequency. So omega C is 2 pi 4.25 K divided by the sampling rate. In this case, the sampling rate is 40K. All right, and so I simplified that to 0.2125 pi. That's omega C. All right, so that was the unknown up here in the desired impulse response. Okay, so next we need to find the roll-off parameter and the length. Okay, so to get the roll-off parameter, we need to calculate the deltas. Okay, so what we know from the Kaiser formulation is that we can look at delta pass. Okay, so delta pass is 10 to the A pass spec divided by 20 minus 1 over 10 A pass divided by 20 plus 1. It's just a formula that we talked about in class. Okay, so you get a number there, 2.878 times 10 to the minus third. So you write down delta pass, then you can calculate delta stop. All right, so the formula for delta stop is a little easier to plug into. It's just minus 60 over 20. Okay, remember this 20, this comes from the definition of dB. All right, it has nothing to do with the Nyquist interval, even though it's half of 40K is 20. That's not what that 20 is for. Okay, and so you do that calculation and you get 1 times 10 to the minus third. So from there, you're just looking at delta. Delta is the min between the delta pass and delta stop. So, as it usually turns out, it's delta stop. Okay? So we know what delta is. It's 1 times 10 to the minus third. And from that, we can calculate A. All right, so A is 20 log 10 of delta. Okay, probably a minus sign there too, which gives me 60. Okay, from there, it's just a matter of looking at the formulas, and I would give those on the exam. So the formula for alpha, for the case where A is equal to 60, is 0.1102, 60 minus 8.7, which is 5.653. So there's alpha. That's done. Okay. Next, we're going to need the length. And to get the length, you need the transition width. And the way this was formulated is it's in hertz. Remember, this is from Orphanatus, so delta F is the same thing as my delta cap F. All right, so delta F is 4.5 minus 4, so that's 0.5 kilohertz. Okay. So there's an intermediate step where you look at the value D. D is equal to A minus 7.95 divided by 14.36. Again, just a formula. You plug in 60 here. The value is 60. And you get 3.625. Okay? From there, you get an exact number for the order, and we know this really should be an integer, so this is in E for exact. That would be 1 plus D times Fs over delta F. Okay? So you plug that in, 1 plus 3.625 times 40K over 0.5K. All right, and you get 290.972. All right, so what we do from there is take this to the next odd value. Okay, so N is equal to 291. All right, so I told you these FIR filter orders can get pretty large. Okay, then the next step is to write this in a MATLAB-like form so that you can get the impulse response. Okay, that's part D. All right, and you did that some with your homework where you calculated the frequency response of a Kaiser filter. All right, so let's run through that. What you're going to need is the delay term, M. M is 1/2 n minus 1. Okay, so you plug in the 291 and you get 145 for M. Okay, so then you can write down a MATLAB-like expression. Okay, sine of, I'm sorry, let me get started with a variable, a vector, K from 0 to 291. Sorry, that's actually to 290, okay, because that would give you 291 terms, right? Okay, so K equals 0 to 290, all right, and then the next step is H is this mathematical expression, omega C, and it's point-by-point multiplication in MATLAB, K minus M, M we've already defined, okay, close that bracket, and then it's point divided by pi K minus M. Okay, and then we continue this line, so it's times. Then we use the Kaiser function. So the Kaiser function needs to know the order. We already know n, and we already know alpha. And technically speaking, you need a prime here. All right, this would be a point-by-point multiplication on the Kaiser vector. All right. Now, you also have the problem that at k equal m, there's going to be not a number generated from MATLAB because you're dividing by 0. So you need to take care of that case specifically. So that would be h of m, but remember with MATLAB indices, we shift everything by 1. So this would be m plus 1. The plus 1 takes care of the MATLAB index. That would be just omega c divided by pi. All right, so we know if we use L'Hopital's rule on d of k, at k equals 0, you would get omega c over pi. Okay? And so that's it. That's the MATLAB-like code that you would write to get the impulse response. And then from there, you could do a frequency check, freq z of h1, because remember, h plays the role of the b's, and a is equal to 1 for a FIR filter. You could put in 1,000 points, and you could put in fs, and you generate the frequency response using MATLAB. Okay, so that runs through it. That's the kind of thing I expect you to be able to do on an exam. I spent this time explaining it. It actually goes through pretty fast if you can go straight through and know which formulas to use.